So the first question is just a joke question. Yeah, what is MPI? If I show the results. So I'm never quite clear. These percentages are slightly confusing because it's never quite clear what they mean when there are multiple answers. But the main thing some of the questions have more than one answer. So there are more than one. Some of the questions have more than one answer. So you may have to more than one may be correct. So but yes. So MPI is the message passing interface, but also a way of doing distributed memory parallel programming. So let's just hope that when we go to the next one, so you should see a new question. Do you see that next question? This is the issue which I had before. But great, okay. So to compile and run an MPI program requires special compilers, special libraries, a special parallel computer, special operating system. So we've got 9. If people could just take a guess. As I said, it's all anonymous, so I don't really know. Okay, excellent. So show explanation. So show results. Sorry. So so most people got it right. I mean, so you don't need a special parallel computer. You don't need a special operating system. All you need to run an MPI program is to be able to launch multiple processes. And even a single core machine can run multiple processes. You computers have been able to run multiple processes for decades. Okay. For efficiency, of course, you need special compiler, but to run an MPI, it doesn't. Now, it appears that you need special compilers because we call them MPI-CC, MPI-F90, or on Archer, they're called Archer 2, it's CC and FTN. But actually, they're not special compilers, they're just wrappers. So you're just calling, on your laptop, you'll just be calling GCC or might be calling Intel CC or something like that. So okay. So that's fine. If you have any questions on any, if you don't understand any of the answers, then please just put a question in the chat. So okay, after initiating an MPI program with MPI run -m for my MPI program, or as we saw on Archer 2, it's srun, but on a standard cluster, what does the call to MPI init do? Does it create the parallel process to start program execution, enable the 4 independent programs subsequently to communicate with each other, create the 4 parallel threads? And often people do very well in this quiz because actually I developed the quiz because I realized there were certain things that people weren't understanding in the course. So obviously the course wasn't as good as it should have been. So I did the quiz and then to talk about this issue. Then of course I sort of adapted the course to answer the questions. But I still think it's useful to go through. They do get a bit harder as we go along. As I said, if you don't know, please just guess. It's completely anonymous. I don't know who anyone is. I don't require you to log in deliberately because I want to be able to, I just want to see what people think. And I should say, actually, I should have said at the start that other than the first question, none of the answers to any of these questions are stupid answers. Every single answer, practically, to every question is a possible answer for a general message passing system. If I'd said, I've got a message passing program and I call MPI and I call start message passing system, what does it do? Any of these 4 answers could be correct. It just happens to be that MPI has a particular choice. So none of these answers from now on are stupid answers. They're all perfectly reasonable answers. It was just trying to find out what MPI does. So what did we do? Okay, so most of you've got it right. Enable the 4 independent programs subsequently to communicate with each other. It doesn't create the 4 parallel processes. That's done by the MPI run. You can actually MPI run a serial program. You could MPI run the LS program, and you'd run 4 copies of LS to list your code. Not very useful. All MPI run does is it runs multiple copies of a particular executable. Hopefully, if that's an MPI executable, it then calls MPI init, and the processes could talk to it. So that's why in the Pi example, I had a print hello world before MPI init to show you got multiple hello worlds. It doesn't create the 4 parallel threads. I'm not normally pedantic about these things. I don't care if people say GNU Linux or Linux, but there is MPI works with processes, not threads. Okay, so there is they are different. It's very important. So OpenMP works with multiple threads. In OpenMP, you launch a single process, 1 program, which at runtime creates multiple threads at runtime. In MPI, you create multiple processes right from the start. I should show an explanation. Okay. Okay, so next question. If you call MPI receive and there is no incoming message, what happens? Okay, so I'll comment on the difference between a process and a thread after this question. Is that okay? So please ask questions. These questions in the quiz are, if anything, primarily designed to promote conversation questions. So that's a very good question. I'll answer it. So anyway, if a couple of you just want to take a guess. We're almost there. I'll maybe give you the answer now. Okay, so almost everyone got it right. The receive waits until the message arrives, potentially waiting forever. The receive doesn't fail with an error. And actually, if the receive, the reason why the receive doesn't fail is MPI is not fault tolerant. So it does. So there are two things here. First of all, MPI assumes all the processes are alive all the time. If you had a message passing system which was supposed to run on a cluster of machines where you were worried some of them might go down or fail in a more cloud-like environment, yes, you would want the receive to time out or fail with an error. But MPI, there's no fault tolerance. So MPI assumes two things. One is you've written the correct program. So if there's a receive, it's going to be a send. So it's quite happy to wait forever. But secondly, it assumes that the hardware is 100% reliable. Now, Dylan asked about processes and threads. So a process is a program, okay, essentially. So I'm currently running multiple programs. I'm running Internet Explorer, right? Firefox, Thunderbird, hundreds of programs, right? And the operating system deliberately makes them ring fence from each other. So my Firefox program cannot access the memory of my Thunderbird program, my email client. They're completely separate, okay? And so that they're completely independent. They're just separate programs. However, a program, a single process, can spawn multiple threads. So you run, and at runtime, it can spawn multiple programs, and they are just like threads, except they can share the memory of the parent process, and that is something a browser might do. A browser might spawn multiple threads to do one thread might be doing animation, the one might be playing a video, another might be waiting for mouse clicks. So within a single program, you can spawn multiple threads, which are like mini programs, but they can all access the memory of the parent thread. So it allows you to have and that allows you to share data. So actually, that's much easier. And you can always tell if a program has multiple threads because it can use more than 100% CPU, because on a modern operating system, those threads can actually run on separate CPU cores. Does that make sense? Is that clear? So threads can share memory. They can read and write to the same memory, which is great for a browser. They could all update the screen and such like, but they all belong to a parent process. So it's the process that owns the memory. Okay, so next question. If you call MPI synchronous send and there's no receive posted, which is the following of possible outcomes. So people are doing very well here, but I do hope you find it interesting. As I said, I do tend to teach the test a bit at the moment for obvious reasons, but they're starting to get a bit more subtle here. So I expect a couple more people have answered, and then just guess. If you don't know, just guess. All the answers again are perfectly possible answers. Any more? Take a guess. Okay, so almost everyone will right. The send waits until the receive is posted, potentially waiting forever because it's synchronous. Now, the message there is actually a send mode in MPI called MPI rsend, which I don't mention, called ready send, where actually the message would disappear. It's there for historical reasons. And again, you might think the send should time out of some specific delay. You might think, well, if I issue a send and an hour later there's no receive, then why doesn't it fail? But again, MPI assumes you've written a correct program. Actually, you can imagine a situation where synchronous send might wait for many hours. Okay, you can imagine that. And so, what would the delay be? And I think it's all these things are based around, again, the fact that the MPI assumes that there is no fault tolerance in MPI. Okay, so the same question, but if you call MPI asynchronous NDI send, which of the following are possible outcomes? So I'm just closing a few windows because my system seems to be very... Okay, so most people have answered. Let's show the results. So, so nobody did a wrong answer, which is very good. Sorry, I'll come back. Sorry. The possible answers are D and F, B, D, and F. Okay. So it is possible the message is stored and delivered later on, if possible, because it's buffered send. Okay. So that is what it's saying. It's saying please, it's like sending a letter. Please take a, or maybe sending an email. Please take a copy and deliver later on. And the side effect of that is the sending process continues execution regardless of whether the message is received. Okay. However, B could also be an outcome. The send could fail with an error. So, in fact, the first time I did this quiz, I didn't have B as an option, and one of the students pointed out B is a possible, and I wrote, yeah, okay, fine. So why is B a possible outcome? Why might the send fail with an error? Memory error, yeah. What do you mean by memory error? I think you're on the right track. Buffer full, absolutely. So that's the problem with B send. The buffer, in MPI, might seem a strange decision that if you want to do asynchronous send, it's up to you to provide the buffer space with MPI buffer attached. And the problem is that you can run out of space. So that's the problem with MPI B send. So clearly, you can see what the next question is going to be. If you call the standard send MPI send and there is no matching received, which of the following are possible outcomes? I think all the answers to 5, I think the answers to 5, 6, and 7 are all the same. The possible answers are all the same. I think that's what I meant. So most people answered. If maybe just I'm losing too many windows here. Just have a guess if you. Oh wait, well, just have a guess if you don't know. It's fine. Interesting to know what you think, because as I said, all of these are perfectly sensible answers. It just happens to be that MPI takes particular decisions on these. Anyone else want to have a guess? If not, I'll just... Okay, show the results. So, the important point is that MPI send tries to give you, it can be buffered or synchronous. So you would expect that the answer to this would be, well, there would be all the answers, correct answers for the previous 2 questions would be valid here. So if it chooses to be synchronous, the send can wait until the receiver is posted waiting forever, okay, which was the correct answer for question 5. If it chooses to be asynchronous, it can do D, the message is stored and delivered later on, and the corollary of that is F, the program continues to execute. However, so that's exactly what I was saying. I said MPI send is able to be synchronous or asynchronous, and you would expect that the outcome would be the union of the previous outcomes, but that's not true. B is not a possible error, a possible outcome here. Why is that? So why was B a possible outcome for buffered send? Because it ran out of buffer. What does MPI send do? Exactly. So it's exactly MPI send. It says I would like to buffer. If you do MPI B send, you're saying, if you do MPI B send, you're telling MPI, you have to buffer this message. That's what I'm requiring. And if the buffer space isn't available, which was up to you to provide, MPI says I can't do it. For MPI send, MPI says, right, I've got the choice of doing buffered or do async. I'll try and do it buffered with a separate, but oh, I've run out of buffers. Okay, now I'll go synchronous. So specifically, MPI send chooses between buffered and synchronous to avoid B, and that's why it's a better thing to do. Now, the downside of it is you don't know if it's synchronous or asynchronous, but the upside is it never fails in that sense. Is that clear? So, Geoffrey said, is that the only criterion to choose between sync and async for MPI? Is that, do you mean for MPI to choose or for you to choose? I think, Geoffrey, that's an interesting question. I didn't quite understand. Yeah, so technically, all the standard says is that MPI send can be implemented synchronously or asynchronously, and so so MPI developers will write their libraries to do it the best way. However, it turns out that in practice, what happens is they use it for this protocol. So for small messages, they're buffered. and for large messages, they're not. But in principle, it could do anything. In principle, it could toss a coin, but in practice, it does that. So James will do. If MPI send is waiting because there's no space in the buffer, but then space appears for another send, does the message use the? I suspect it doesn't. I mean, in principle, it could, but I suspect, and these are all implementation questions, but I suspect it takes the decision at call time. It says, can I buffer this message? No. The idea is that by the time that synchronous send has finished, some of the other asynchronous sends might have freed up buffer space. I doubt that it will change. In fact, it can't. It can't, probably can't. I mean, it's a bit of a technicality, but what happens when you have synchronous send is that rather than sending the whole message, it sends a little header. It sends a header. So look, I've got a message for you. When you're ready, come back and I'll give it to you. And I suspect once you've decided to send a little header, you know, an acknowledgement to somebody that I'm ready, you can't then back out. I mean, in principle you could, but I suspect in practice it's too difficult. Does that make sense? It's a good question, though. Okay, so that I've just said. So as I said, if the difference between synchronous and asynchronous could cause deadlock, then you must take another approach, e.g. using the non-blocking or immediate form MPI send. So that's okay. Next question. The MPI receiver routine has a parameter count. Actually, somebody asked about this, and so we may have discussed this already, but you may not remember. But if somebody did ask about this, the MPI receiver has a parameter count. What does this mean? The size of the incoming message in bytes, the size of the incoming message in items, the size of the buffer you've reserved for storing the message, the size of the buffer you've reserved for storing the message in items, in bytes or items. I've used integers here as an answer. So it's for people to have a guess. If you don't know the answer, it's useful to know what you think. So I'll show the results now. So, okay, so you would think it's the size of the incoming message, but it's not. So first of all, it's not the size of the buffer you reserve for storing the message in bytes. It could be, but MPI really tries not to talk about bytes. Because once you start talking about bytes, things become non-portable because you have to assume things. So MPI tries to talk about items, not bytes, where it can. So you'd think it would be the size of the income message in integers, but it isn't. It's the size of the buffer you reserve for storing the message. So what you said is, I would like to receive a message from somebody, and I have got enough space to receive. I've reserved 10 integers to receive that message. Now, in many programs, that is the size of the incoming message. Yeah? I mean, Mohammed said the size of receive except to send message can be different. That's exactly the next question. So I'll come on to the next question. So the size thing. So actually, you're not mandating what the message size is. You're saying, I'd like to receive a message from you, and I have this much space to store it in terms of integers. But in many programs, those are the same. Okay, so this is a subtlety which many people don't appreciate. Because in many programs, you know, you're sending 10 integers, you're receiving 10 integers. In the Pi program, we were sending 1 integer, receiving 1 integer. But in general, that's not the case. So the obvious question is there, what happens if the incoming message is larger than count? So anyone else want to have a guess? Okay, okay, this is interesting. So actually, the receive fails with an error. So see the message writes beyond the end of available storage. MPI tries to be safe. You know, it doesn't like things like that. So MPI, where it can, will do error checking. So it doesn't do C. Now D is a very interesting answer. You can imagine D, but there's a problem there. If D was the right answer, so imagine I do an MPI receive and I say count equals 5, and the incoming message has count equals 9. If I only receive the 5 items, then there's 4 which haven't been received. And that means well, what do I do with them? My program won't be correct unless I receive them. So I'd have to issue another receive. And remember, once the receive is complete, that's it over. An MPI, that isn't the model for MPI. In MPI, a single message matches a single receive. So you can't partially receive messages in MPI. That might not be obvious, but so it's very much a single message, a single send matches a single receive. If you wanted to implement D, you'd have to flag up that you'd have to receive them and have a flag saying, by the way, there's more, you'll have to post another receive. But that's quite awkward, and that isn't the model for MPI. So MPI strictly matches a single send with a single receive, either successfully or unsuccessfully. But there's just, it either matches or it doesn't. There's no in between of partial matching. So the receive fails with an error, and it's one of the few places in MPI where you get a useful error. You'll get something like buffer too small or something like that. Okay, and the obvious other question is, what happens if the incoming message of size n is smaller than count? That's the obvious other question you might ask. Show the results. So so the receive doesn't fail with an error. MPI is trying to let you trying to let you receive a message of arbitrary size here. The receive fails with an error, so it doesn't. In fact, the first n items are received. You could imagine the first n items are received and the rest of the storage is zeroed, but there's a number of reasons why that's probably not a good idea. But in fact, to be honest, it's probably just performance. I mean, MPI is written to be fast. So if I have a 10 megabyte buffer, receive buffer, and someone sends me an integer of size 1, and I receive it, if I go away and zero that megabyte, 10 megabytes of storage, it's going to take a long time, and it's not necessary. So it's partly because you can imagine programs where you would want to, you would want to receive some data and fill in a buffer and not touch the outside. That's actually quite rare, but you can imagine it. But actually, probably the real reason is that it would just take a long time. But the important point is, there are occasions when you don't know how many items you're going to read. So let's imagine we're doing a crowd simulation. We've divided our domain. We might be simulating a sports stadium. We've divided our sports stadium onto blocks. Each process is responsible for an area of the sports stadium, and it has people in it. Well, as people move around, they'll leave that area. So every iteration, as I move people, I have to tell my neighboring processors, hi, I've got 7. Now, unlike the traffic model, we don't know how many we don't know how many people are going to move. So I need to be able to send, say, look, send a message of 7 people up the way or 5 people down the way. MPI is trying to let you receive messages of our. Now, in fact, of course, you have to be able to bound it. But in many simulations, you can bound it. You can say, look, there will never be more than 1,000 people leaving any domain, and therefore, as long as I have a receive buffer size of 1,000, I'm happy. As we saw, if you are worried about that, there is this MPI probe. Okay, so I've issued a receive. I've said count equals 10. A message comes in, and it's been received. Technically, all I know is that the incoming message had a size of 10 or less. How do I actually get the actual size? So I've issued and said, look, I want to receive all the people that have moved from your domain to my domain. It's never more than 1,000, so I reserve a receive buffer of 1,000. I receive the data for all the people, but clearly I need to know how many people have been received. Otherwise, I don't know which parts of the receive buffer unless I know how many elements I've received, I don't know parts of the receive buffer are valid or old data. So yes, in status, I mean, yeah, fine. Does anyone else want to guess, and I'll show the results? Okay, so there's a few questions coming in just to check. Oh, okay, fine, sorry. So the value of count. So MPI cannot tell you. So if MPI couldn't tell you, it'd be very hard to write it. So you're correct, it's stored in the status parameter. So that's it's not. You could put it in the tag. I mean, you could tag all your messages, but in fact, MPI tries to be friendly here. So you have to do MPI get count. It's not directly available in the status. You have to actually. So it's useful to it's not a valid question in MPI to say how big was the incoming message, because if I've received 4 integers, if I defined a type of block 4 which was 4 integers, that is one block 4, or it's 4 integers. So that's why you have to pass the status to MPI get count. You have to say how big was this message in terms of integers. How many big was this message in terms of, so that's one of the technical reasons why the count isn't available as a direct. The tag and the source are direct members of the structure of the status parameter, be it a structure in C or a little array in Fortran. Okay. Some other, which of the following possible outputs from this piece of code run on 3 processes? Print welcome, print goodbye. That's all I've done. This is formatted slightly strangely, but I don't use hello because hello is different. Like welcome and goodbye have the same number of letters. That's one reason. So which of the following are possible outputs from this piece of code? Okay, so I'll show the results. So they're very good. Okay, so well, A, C, and D are all possible answers, but B isn't. Why isn't B a possible answer? They want to say why that is the problem. So goodbye before welcome. Yes. So goodbye before welcome. Right. So rank 1 does. So the important point is that when MPI print, I mean, it's actually the MPI run or whatever the launcher program, which it's quite complicated. If you launch 1,000 processes and they're all printing to the screen, of course they're not even attached to the screen. They're running on some remote system. So the standard outputs are all collected back to the MPI run program, which munges them together, and it's guaranteed that the output from any particular process appears in order, but they could be put together in any order whatsoever. And the order has no significance as to what actually happened. So just because you see welcome from rank 2 before welcome from rank 1 doesn't mean this print statement was issued before this one. Who knows? But it is very important that the output from any particular rank appears in order. And that's true for A, C, and D, but not true for B. So that's basically what I'm saying here. The next one is, okay, so which of the following statements do you agree with regarding this code? They're getting a bit more abstruse here. You often see this, people say, I'll loop over process, rank equals no, I less than size article. If rank equals I, print hello from rank whatever, and j equals 10 times I. So a couple more people, just have a guess if you want. I don't, it's fine. If you don't know the answer, just have a guess, and I will show the results. Okay, so a lot of people got it right, actually. For loop is entirely redundant. This is very important, right? So why is A not correct? Why is A, the for loop is the operation in order, right? Why is A not correct? There's no barrier. So because there's no barrier, there is, remember, this code is running independently on different processes. Rank 3 could encounter this code at 2 p.m. this afternoon. Rank 5 could encounter it at 10 p.m. at night. There's absolutely, the MPI programs do not execute synchronously across processes unless, as Matthew has said, you put a barrier in. But by default, they're running completely independently, so it does nothing about the order. However, you're absolutely right. If I put a barrier in, it would, if I put a barrier in, I could make sure that the print statements were executed in order. Unfortunately, that doesn't mean the print statements appear on the screen in order, because who knows, but okay, fine, but that's just. The for loop ensures the operations are done in parallel across all processes. Why is that not correct? So that's what people often do. They think, I'll do this, okay, but why is B not correct? Again, so B looks like a sensible answer, but it's not correct. Why is B not correct? Anyone want to? But it's not correct because MPI programs are parallel. Exactly, it's not necessary. MPI programs are parallel. MPI programs are parallel all the time. This loop, all these statements are run in parallel by default because every process, it's SPMD. Every process is executing every loop. And the final variable j will be 10 times size minus 1. That's not true. That would require j to be a shared variable across processes, but it's not. Every single process has its own value of j. So in fact, all this stuff. Now, to get this is equivalent to me saying, imagine we were in a classroom. I had a class list, okay? And we'll have all our names on it. We've got Jove, Matthew, John, Helen, me, okay, on the list. Okay, so I'll come back to this. So we've got this class list, and I've given it to all of you. And I've told you all, go down the class list until you see your name, and then say hello from your name. So I go to David, hello from David. That is identical to saying just say hello from your name. Yeah. So this loop is entirely redundant. Okay. Would it be sufficient for j to be outside the if? Yes. Then j would be equal to 10 times size minus 1 on each. Correct. But again, yes, that's correct. You're right. You're correct. But people sometimes think that j will be 10 times size 1 because they think j is like a shared variable, but it's not. Okay. So that, you often see this kind of code, and normally it means that people haven't understand the SPMD model. It's important to the for loop is entirely redundant. Okay. And you very, very rarely see write code like this. The only exception is if you're maybe doing a gather, you're looping over everybody and receiving data, that you should use a gather. But that's quite okay. So it is important to understand the for loop is entirely redundant. This is exactly the same as saying print hello from rank var j equals 10 times rank. Okay, there is no difference between that. Except this is slower because you've got this redundant for loop. Final question. Apologies for the Fortran programs, it's in C, but hopefully it's fairly legible. What is the output of this MPI with 8 processes? Are you running on ranks 0 to 7? So if rank percent 2, that's the same, that's the mod operator if you're a Fortran player. So the even processes do MPI reduce of their rank into even sum, which is one MPI int, MPI sum, MPI world, and they print their sum. Else the odd processes do an MPI reduce. It's the same thing except into odd sum, and they print odd sum. Okay, so what's the output of this code on 8 processes? Is even sum is 16, odd sum is 12, even sum is 28, odd sum is 28, even sum equals 12, odd sum equals 16, even sum equals 6, odd sum equals 22. So what you're doing is the even processes are adding up their ranks and storing it in even sum. The even process calling MPI reduced with their rank and putting it in even sum, and the odd processes, which is 1, 3, 5, and 7, are calling MPI reduce with their rank and putting it into odd sum. So I'm going to come back to that, Matthew. That's exactly what I'm going to come back to. Yes, but so that's the point of this question, actually. But I'll come back to that. But first, we'll answer. So what do you think the answer? Well, you can put your answer in for this. Yeah. If you don't know, just take a guess. Okay. Any more for any more? Okay, so the code is written to make you think that it's actually even sum would be 12, 0 plus 2 plus 4 plus 6. Or, okay, the code is written to make you think it's either it's A or C. It's C, and if you get even or the other way, it's A. Okay, fine. But it's not, it's B. Why is it B? And I see quite a few people got that right, which is good. Why is it B? So the code, this is the closest thing I have to a trick question. The code is written to make it look like the answer is yes. So it uses MPI com world. So in fact, okay, all the processes, in fact, the point is that well, it's not because it's all reduced, it's because it's com world. So the all reduce function, okay, well, because you're calling on com world, this line, yeah, and this line match each other. These are the same. The fact they're called from that. Normally, when you call an all reduce, you'll be calling it from the same line of code. But actually, the fact that all reduce can match that one as well. Okay, because MPI is a library. It doesn't know what line of code it was called from. Okay. Yeah. Well, I don't. So a process can be called by MPI even in a line it does not have access to. No. The even processors are calling this, and the odd processors are calling that. Okay. The only difference is that it's like me saying if your birthday is an odd day of the month, yeah. Okay. Okay. The answer is scattered. Well, yes. So all this is saying is you're adding up but the even processes are choosing to store the result in a variable called even sum, and the odd processes are choosing to store the result in a variable called odd sum. Okay. So you're doing an all reduce across all processes. Okay. So does that make sense? So this is a bit of a trick question, but it is important to realize that each process is only executing one all reduce. Luckily, all the processes are executing all reduce, so it doesn't deadlock. Okay, and so they're all executing the same all reduce. It just happens to the even processes choose to store the answer in even sum, and the odd processes choose to store the answer in odd sum. Now, if we want to do this, how would we? I haven't told you, but yeah. So we can create two different. It doesn't matter if they're separate calls. And if you think about it, how does MPI know they're separate calls? How does the MPI library, a function doesn't know what line it was called from. Well, it's got a return address, but a function just says somebody called me. Yeah, it's just a function call. Doesn't know where it was called from. Why would it care? And of course, you want this flexibility because you might be calling different functions and then so this is flexibility you don't often use, but it's there. And so what you could do is you would create two communicators. So you'd have you would do, and I didn't go into the detail, but that's why MPI or these collective communications take a communicator. It allows you'd have to create a communicator where you'd have to create a communicator with one which contains the even processes and one which contains the odd processes. So you'd create two communicators. And MPI com split is the most general routine for doing that. I didn't give you the but MPI com split allows you to split a communicator into multiple portions actually. So yes, one communicator for the even rank and one for the odd rank exactly. So that was the answer there. So I hope you found that useful. We've gone slightly over time, but there's some chart here I never understand. What we're going to do is we're going to do hopefully work on a code which is the simplest thing closest thing I could get to something which is a combination of being simple enough to, I mean, maybe not complete in an afternoon, but simple enough to be tractable based on the MPI but actually be representative of a real program, a real scientific and technical program. So, okay, I think fine. So, what we're going to do is we're going to start with a big array. So actually, this program is parallelized conceptually identically to the traffic model. We have an array, and we split it up between processes, and we have halos for the edges. However, we're going to use a 2D array here, not a 1D array. And what we're going to do is that's going to represent an image. We're going to do an image processing exercise. So this array will actually be an array of pixels, but it's just an array. And we're going to split it into pieces. That's how we get parallelism. And we're going to assign pieces to processes. So process 0 has that piece, process 1, process 2 that piece. It turns out that just like the traffic model, the update equations, the algorithm we're going to apply to this image requires comparing each pixel, combining each pixel with its 4 neighbors, up, down, left, and right. Now, importantly, we've decided to split this this 2D grid up into slices. So the parallelization is identical to the traffic model. Okay? We have a line of process. You could choose to split this image into a square grid, but that would be a lot more complicated. You can try that if you want, but initially we're going to do a simple split this 2D grid into slices. Now, the update equation we're going to do for the pixels is going to require comparing each pixel to its 4 neighbors. And that means we have this issue that this process here, it needs to know that pixel, that pixel, that pixel, that pixel. Well, it's fine, but up here, the pixel it wants to know up here or down here will belong to this process. And exactly like the traffic model, we are going to use halos to deal with nearest neighbor interactions. The difference here, though, is that the halos are complete lines of pixels, not just one element. So what we're going to do is that before this process does any update, it's going to receive the boundary data from process 2 into this halo, okay? And the same from the green process here, and it will also send its boundary data to there and to there. Now, having done this halo swapping, again, completely analogous to the traffic model, we can then do one iteration of updates to the pixels here. But for the next iteration, we need to do halo swapping again because the values of this here will have been updated by process 2. So we do this communicate, calculate scheme, just as we did with the traffic model. So what are we going to do? Well, I've picked an edge detection algorithm just for fun. So what we're going to do is we're going to have a very simple algorithm which does edge detection. So here I've got a picture of William Wallace, played by what's his name? Gibson. I can't remember his name. My brain's gone completely to mush this morning. Played by this famous Australian, and I've not actually seen Braveheart, I have to say, but it's a very famous film in Scotland. At least it's very popular. William Wallace did something which makes you very popular amongst Scots. Apologies to English people here, but I'm English, so I can say he killed a lot of English people a long time ago, over 700 or 800 years ago. Anyway, so Mel Gibson, of course. What we're going to do is we're going to have a very, very simple edge detection algorithm, which if I apply it to this image, gives this hint. And it actually looks quite well. It's picked up the edges quite nicely. You can see his sword quite nicely and such like. The problem is that to do an edge detection is a single pass. We pass through the image once and we get the answer. That's not worth parallelizing. Because what you're going to have to do is you'd have to read in the image, scatter it to the processes, do one pass through the algorithm, gather the I mean, it's pointless. It's not worth parallelizing. However, it turns out, it's a slightly fake thing to do, but it's quite fun, that you can actually reconstruct the images from the edges. So I'm going to provide you with edge images, and you're going to have to reconstruct the actual image. And it turns out that that requires hundreds of iterations. So it's worth parallelizing, okay? It's a slightly fake thing to do, and it's not immediately obvious you can do it, but for the simple edge algorithm I'm going to use, you can reconstruct the image from the edges. So I'm going to give the edges, and you have to reconstruct the image. And I'm doing that because it takes hundreds of iterations. So edge detection, the simplest edge detection algorithm you can imagine is to compare the value of a pixel to its 4 nearest neighbors. So the pixel values are 0, black to 2 to 5, white. We define the edge to be the sum of the pixel to the right, up, left, and down, minus 4 times the image. So you can see that if the nearby pixels have a similar or the same value as the current image, this value is 0. But if the nearby pixels differ a lot, if the average of the 4 neighbors differs a lot from the current pixel, then this gives a finite value. So you're just saying, are the values of the neighboring pixels very different from my current value? If they are, that's an edge. Okay, so that's actually quite straightforward, and bizarrely, it actually gives you quite a nice edge. The simplest thing you can imagine doing. You might ask, what are the boundary conditions? What happens if I look for a pixel up here or right here? Well, I'm going to do exactly as this picture suggests. I'm going to surround the image in a sea of white. So the image is embedded in white. So we use non-periodic boundaries. Periodic boundary conditions don't make sense for an image. But with pixels off the edge of the image, e.g. image m plus 1, j are set to white. So we pad the 2D array with halos, and in the serial code, all the halo values are set to 255, i.e. white. So what would happen here is, there's actually a halo up here, and we set that to white. There's a halo down here that's set to white. There's a halo here which is set to white, but some of the halos are updated. But all the halos around the boundaries are set to white. So the image reconstruction is actually, so this is the edge just defined as this, the up, down, left, right, minus 4 times the central value. It turns out that if we repeat this operation many times, we take a guess, and we call that old, and we say the new pixel ij is a quarter of the old right, down, left, up, minus the value of the edge, divided by 4. If we repeat that many times, we can reconstruct the image from the edge values. Now that's not obvious. However, if you have got, you can ignore the next few minutes or so, but if you've got a physics or applied maths background or an engineering background, you might recognize as saying that that is the edge, is grad squared image. That is saying the edge is the second derivative of the image. And that's actually a sensible thing to say, because if the pixels are changing uniformly, then there's no edge. But if there's a second derivative, they're changing rapidly, we'll call that an edge. So actually, we're solving edge is grad squared image, so we're solving grad squared image equals edge, and it turns out you can do that. But that's irrelevant in terms of this exercise. All we're saying is we repeat this many times. You guess an image, and many times you update new. And this again is very, very similar to the update equation for the traffic model, except we have 2D, except for 1D, but it's very similar. We'll repeat this many times. In parallel, you must update the halo values from neighbors every iteration, but in serial, you just do this. So we're going to do a domain decomposition. Now, it turns out in C and Fortran, it's best to do different domain decomposition. So in C, so I goes along and J goes up the way I've drawn it here. In C, we split along the first dimension. So all processes have every value of J for the image ij for a subset of I, but in Fortran we do it differently. We say that every process has all the values of I for separate values of J. Why do you, now you don't have to do that, but if you choose this decomposition, you decompose the first dimension in C or the second dimension in Fortran, we get, and the image is of size m by n, we get a much simpler program. Can anyone think of why that might be the right thing to do? There's a couple of reasons. Yes, so exactly. Contiguous memory. What do you mean? You've got the right answer, Matthew. Yes. So why does that help? What do you mean by contiguous memory? It's the right answer. I just thought you could maybe explain it a bit more. What's contiguous in this sense? So the important point is we're going to have to swap, the values. So we're going to have to swap all the values along the halo here. So in the C example, those are lots of values of J for fixed I. So that boundary is contiguous in memory. So we can send and receive it with a single send. Okay. In Fortran, because of the opposite ordering, all these values are varying values of I for fixed J, so that's a block of memory. So we can also swap that. Now, we could decompose the Fortran one that way. So no, compilers, I didn't quite understand how do compilers try to fix this? Compilers are very dumb. They just do what you tell them. So compilers can't switch the memory allocation. It's defined in C that xij is next to xij plus 1, and it's defined in Fortran. Oh, well, it's not the I and the J loops. So it's not the loop. It's the storage order. So yes, compilers can't. So that's a good question. You're right. So for a standard loop, if you loop in the wrong order, then a good compiler will say that's stupid. I don't want to loop I then J. I'll do J then I, or the other way around. However, this is a separate question. We're asking about where is the data stored in memory. And that cannot be changed by the compiler. That's fixed by the language. So you're absolutely right in terms of efficiency of looping over the indices. You shouldn't have to care if you do I, do J, or 4I, 4J. A good compiler will, well, you ought to do it the right way, but a good compiler will spot it and switch it around. But that's not what we're talking about here. We're talking about how the data is stored in memory, which the compiler cannot change. Is that clear? You're right. They're related concepts, but they are different. Yeah. There's another example that actually, if we divide the arrays up like this, we can distribute the array to all the processes with a single gather and a single scatter. Because remember, gather and scatter distributes equal blocks of contiguous memory to each process. If we've just divided the arrays in this fashion, then remember, thinking of it as a linear array, the first quarter of the array goes to the 0th process, the second quarter to the second, and the same in Fortran. So there are actually two reasons why it's a good idea to do. So I provide you with more detailed printed instructions, a tarball with input and output written into a couple of input files. So the task is to write a serial code and check it works. I'll actually provide you one here. Then distribute the work onto the processors, but do separate reconstructions. What I mean is, the first thing is distribute the data to the processors, but do a separate image reconstruction on each process, but don't swap the boundaries. Just separately reconstruct the image. What do you think you see when you do that? Anyone guess what you see? So you're doing an image reconstruction of the local image, but you're not talking to your neighbors. You're just doing it locally. And I like image processing examples because it allows you to see bugs and issues visually. What do you think you see if you did an image reconstruction like this, where each process did a single image reconstruction, but we didn't exchange boundary data? What do you think you might see? Exactly. So you actually see lines. So you actually see these lines on the image. Exactly. Artifacts at the boundaries. It looks okay, except there's big white lines down the edges. Then get the headers exchanged a single reconstruction. You should get an identical answer to your code, and there's further suggestions on the sheet. Now, this is an issue here. The images are sort of very old text-based format called PGM, which is easy to read and write. Unfortunately, I just discovered that since I last ran this course, the image display program has disappeared from Archer 2. It was rebuilt. So apologies. So I'm going to sort this. If you've got a Linux machine, you'll be able to install. So the problem is PGMs are such old formats that most image programs can't view them. So I will address this so apologies for that, but I wanted to do a quick poll. So could people say what their laptop is? So if everyone could answer, it would be very useful. So I think we have a subset, but for Linux, you can just install the ImageMagick suite, sudo apt install ImageMagick. Windows and Mac, so unfortunately, you're going to have to copy the files locally and view them locally. Apologies about that. I will try and get something installed on Archer before lunch, around lunch, which fixes that. But I apologize that I hadn't quite. So MOBA X term. Good question. I don't know how you install. So if the image viewer were installed on Archer, then you would be able to. What I would like you to be able to do is to run the image viewer program on Archer 2, and then no matter how you've logged on, MOBA X term, Mac, Linux, you would see the image locally. The problem is we do not have the image viewer program I need on Archer 2. You're going to have to copy the file locally and view it locally. And I don't know whether within MOBA X, that's a good question. I don't know. And so apologies for that. I will try and fix that. I hadn't quite checked. Okay. So I will very briefly show you the walk you through the exercise sheet very quickly. So separate exercise sheet here. So it goes through the same stuff that you've seen. It shows you this example. Interesting, actually, I don't think I can do this here. This is something I like to. Let's just show an actual viewer. I don't distribute this image because someone once asked me, do you have copyright on the mail given? I was like, no, I don't. But anyway, if I zoom in on this, I don't know if it's obvious. Can you see something funny on that image? I don't know how well it comes out, but if I do an edge detection, can you see something weird? Furry, yeah. But what about up here? What can you see there? Squares, exactly. So I thought that was a mistake, but they exist. So there is a background of squares in this image which you can't see very easily, but you do edge detection. You can see. Anyone know can anyone think what that is? Why that is? No, now green screen. That's not green screen. It's to do with the image format. No, not the halos, because the halos are just this. You get the same answer whether you do serial or parallel. JPEG, exactly. So this has been some point been stored as a JPEG. JPEG is a Fourier transform method which works on blocks, and it throws away the high frequencies. But you get artifacts at the block edges, and I think the standard block size is 32 by 32 or 60 by 60. I can't remember. You can actually see that. You can actually see that on the image, which I'd not noticed before. Anyway, that's fine. This just goes through this. So I try. Remember that you need to have halos. And in Fortran, it's very nice to declare. In Fortran and C, you should declare your arrays to go from 0 to n+1 and 0 to n+2, which you can do in C and Fortran. So this is pseudocode, but it's almost identical between C and Fortran because I want you to declare the arrays in that way. And then I talk about the parallel program. So, and there's lots of exercise. So what I would just like to do is I'll just really briefly just show you how this works on my laptop. So if I right, so I will share my so what I'm going to do is I'm going to copy the this is the code I give out. Unfortunately, I've copied the. Remember, this is an annoyance with Git where you have to replace blob with master. This is what I and I give you some images, these edges. So if I can you see that? You're not seeing that, are you? Sorry about that. That didn't work. Give me a second. Where is it? Okay, so what I actually did was I did a wget of the code from Archer from the website, and then I unpacked it. And then I went to, you'll be doing all this on Archer, it's on my laptop, and you'll see that I've given you some files for doing I/O and such like. But I do have some. So in fact, the default application I want you to work on is this thing. So there's some weirdness here. Sorry, I'm messing this up. So, okay, I'm having some. Okay, so I'm not able to show you the images at the moment. There's some slight problem with the image. Apologies about this. I will fix this. The image display stuff. There's something. As I said, the problem is that to be able to read and write images, I use a very old-fashioned, simple text format called PGM. But unfortunately, it's not particularly well supported anymore. So So you should be able to do the exercise. It will work. It's just that you may not be able to display the images. It's a shame. I'm going to fix that between now and lunch. So apologies about that. So sorry that today's been a bit lecture heavy, but I'm not. I will come back at 11. I'd hoped you'd had a bit of time to play around with the case study. You have half an hour of a coffee break now, but I'm going to come back at 11, sorry, 11:30, apologies, 11:30, and give the final sort of lecture, which is tips and tricks. And then this afternoon will be free for you to do the case study and ask questions for people who'll be around to answer. So I will fix the image display stuff as soon as I can. Apologies for that. I'll go through this lecture relatively quickly because I used to give this lecture a different name. I can't remember what I called it, but it is basically a bunch of things which you might encounter when you're writing real MPI programs, and some of them may be interesting to some people, some not to others. So I'll go through them quite quickly, but please, at any point, if you have a particular question, then just ask in the chat and I will see it. So, I'll go through these things fairly briefly. There's about 30 slides, but it's really just a sort of, we can pick up on various points that you might want. So there's a whole bunch of stuff here. But what I'll do is, the aims of any of this course are to allow you to write portable MPI programs, portable to many systems that are efficient and easy to maintain. And just a bunch of different issues that people come across and various solutions and such like. So I'm gonna, common problems which I'm going to cover in assuming the MPI send is asynchronous. I've talked about ad nauseum, data sizes, non-portability, specific process counts, collectives, non-blocking, lots of small messages, array allocation issues in C, array syntax issues in Fortran, code readability and debugging. So I'm going to go through these, relatively quickly, and you'll have the slides. Albeit there is a recording of this lecture, but please, if you want more information as we're going through, just ask a question in the chat. Okay. So I've said this a lot of times, but one of the biggest issues with MPIs is that people assume MPI send is asynchronous, which leads to potential deadlock. It is often buffered for small messages, but the threshold may vary with the implementation. And so you would potentially get the worst bug. Your code may run on one machine and deadlock on another. And typically, very large systems will have smaller internal buffer sizes, whereas your laptop will have a big one. So you very often get a case where someone's code runs on their laptop, deadlocks on Archer 2. They say Archer 2 is broken, but they've assumed that MPI send is asynchronous. So that a correct code will run with all MPI send calls replaced by MPI send. So that's always the thing I say to people. Your code runs on your laptop, it doesn't run on Archer 2, replace all your MPI sends with MPI sends, and if it deadlocks, then you have an incorrect program. Again, if you do use MPI bsend, the default buffer space may be 0, you have to use MPI buffer attach, and you have to add this. It turns out if you've got MPI bsend overhead, you have to add something extra to the buffer. So it's all a bit horrible, but this is the major problem that people have in portability. They assume MPI send is asynchronous, and it's not guaranteed to be. Data sizes, be careful of data sizes or layouts. For Fortran, if you're a very pedantic Fortran programmer, you should use the runtime inquiry functions for Fortran types. The Fortran 2008 solution to the Pi example shows you how to do that. Be careful of compiler-dependent padding for structures. Just because the compiler on your laptop doesn't put padding into a structure doesn't mean that another compiler might not. So you need to be careful with that. Don't use magic compiler flags to change precision. People write code using floats and they want to use double, and so they do CC minus convert floats to doubles. No, don't do that. It's a world of pain, because when you change float to double, you also have to change MPI float to MPI double as well. So don't rely on magic compiler flags to do these things. But actually, you might say, well, I want to have a program that can run in single or double precision. How do I do that? Well, you should do it with an include file. You should have a precision.h file. So in C, you should define a header file called precision.h, and nowhere in your code you should say float or double. You should have type def float real number, and everywhere in your code you do a real number x. And if you say type def float real number, that's a float. Type def double real number, that's a double. But you do the equivalent for the MPI types. You do have to find MPI real number, MPI float. So you do real number x, MPI routine address x, MPI real number. And then if you want to change it, as long as you're consistent that everywhere in your code you use this convention, you can change. You just in your precision.h, which is this file here, you change that to double, that to MPI double, and you recompile, and it's done. So that's the way to elegantly, but don't. Or you could use templates. Yes. So this is an old-fashioned way of doing it. If you're using C++, you could use templates, exactly. So you would match a routine which took a float would call the correct MPI. So this is because C doesn't have that overloading that you can do with templates. In Fortran, it's exactly the same, but you use Fortran's type system with has a more sophisticated type system. You do the same for real number, but you have this real number equals kind of 1.0 E0, and then you would just change that to 1.0 D0. But that's the important. You need to, if you want to be able to switch precision, you need to be able to do it properly, and don't just use magic compiler flags, because the compiler on another system may not support them. So, and with non-portability, I mean, a correct C code should compile correctly with any C compiler. A correct MPI code should also run correctly with any MPI library. So you should check portability as you go along and run on more than one machine. That running on two different machines isn't actually a good test if the MPI libraries are the same. I'm assuming you want to use different MPI libraries. So many parallel clusters will use the same open source MPI. So many machines you run on will use OpenMPI. So running on two different HPC systems may not be a good test. What's actually much nicer is running on more than one implementation on the same machine. So run using both MPI-C and OpenMPI on your laptop, for example. So install two versions of MPI on your laptop and check your code works with both of them. And so, for example, if you're lucky, your cluster will support different compilers and different libraries. But just as I'm saying, to check you have a portable C code, you should regularly compile it under multiple C compilers, not just run it under GCC for 10 years and then wonder why it doesn't compile under Intel C. You should also regularly check your MPI program runs correctly against different MPI libraries. And if you can have two MPI libraries on your laptop, the obvious ones will be OpenMPI and MPI-CH2, then that's very nice for doing debugging. Code readability, this is a big, adding MPI can destroy your code. The serial Pi code was a few lines, the parallel one was 50 lines. We'd like to maintain a true serial version. This is good for debugging as well. You get the wrong answer with your parallel code. Well, what's the correct answer? Well, the correct answer, your gold standard, is probably your serial code, but you may not have a serial code. You may have put lots of MPI calls into your code. I really mean running a serial code without an MPI library, not running on one process. So the way to do this, and it's an elegant way of programming, is to separate off the communication routines, put them all on a separate file. So you don't call MPI routines from your main program. You call your own communications routines, which can have much more sensible names than the MPI ones, and you just provide two interfaces, one for serial, one for parallel. So a very well written MPI program has no explicit reference to MPI in the main code. So just to say an example, initialization, okay? To initialize MPI, you do MPI init. These are in Fortran for historical reasons, but it's exactly the same in C. MPI com size, MPI com rank. This is horrible and ugly, okay? It's much nicer to have a routine called power begin. All I really care about, all I cared about in this program was I wanted to start my parallelism, and I wanted to know how many processes there were and what my ID was. And actually, because this was a Fortran program, I wanted the ID to start from 1. So I called MPI com. I actually started in my main program, the IDs were referred to from 1, which was much nicer. So, you know, all this horrible MPI stuff here in my code now becomes call power begin size proc ID. That's much neater, and you implement it with MPI. And then for a serial routine, of course, it's trivial. Size is 1, proc ID equals 1. Much more illustrative is a global sum. To do an all reduce for global sum and do an all reduce for double precision number is horrible in MPI. Call MPI all reduce dval dtemp 1 MPI double precision MPI sum com, then dval equals dtemp. That's horrible. I'd much rather call a parallel. In my code, I do call power d sum of dval, which does a parallel distributed sum of double precision value. That's much neater code. It looks much nicer. It's much more readable, and I implement it with MPI. And of course, for a serial machine, this is a trivial routine, so I don't need to do anything. So this makes my, as well as allowing me to run on with MPI or without MPI, it makes my MPI code look much neater, because the MPI code has call power d sum of dval, and it hides all this horrible MPI complexity. So that's a really good. Now, people used to do this a lot 20 years ago, 30 years ago, when MPI wasn't dominant. People wrote had their own communication stubs and implemented them in MPI or whatever message passing library was available. That people have sort of forgotten how to do that, because MPI is all available. Just because MPI is always available doesn't mean you should sprinkle random MPI routines in your code. You should say, you know, this is a much nicer way to program. And again, if you have whatever build system you use, but with a good make file. Now, for some reason, I had 2 libraries, dem parallel and dem coms, not 1. But I had my sequential source, which had no explicit references to MPI. It only called my own routines, power begin, power d sum. I had a power halo swap routine, and I implemented them in MPI in these 2 routines, or the fake versions were here. And all I have to do to get a serial version is replace parallel source as MPI source with parallel source equals fake source, and I can compile. And it's a very good way of programming to do that. And there's lots of advantages. You can compile the serial program from the same source. It makes parallel code much more readable, because your parallel code has meaningful function calls. Halo swaps, double precision global sums, initialization, final, not random MPI calls which don't make any sense to anybody. In principle, it also allows you to code to port to other libraries. If someone said there's a magic routine to do very fast double precision or global reductions on the Cray, instead of calling MPI within this interface, you could call your own. You could call this magic Cray routine, and you wouldn't have to change your main code. It would just be, now in practice, MPI probably uses the most efficient method now, but it's still useful there. The other thing is your library can be updated to optimize for different MPI calls. So for example, if I have a halo swap routine, so my main code just says halo swap, you might say, well, should that be done with send, send, bsend, send receive, I receive send, I send receive, I send I receive? What should I use? Well, you could implement your halo swap routine in a number of different ways, and you can find out which one is fastest just by trial and error. But your main code doesn't have any MPI. It just does the natural thing. It calls a halo swap function, and you implement that whatever way is best. So there are a lot of advantages to have your communications library. So are there any questions about that first section, which is really about sort of coding style? Okay. So, okay, a classic thing is not calling collectives. All collectives must be called by all processes in a communicator. This won't work on more than one. You know, if rank equals 0, call MPI bcust. On all reduced, it would definitely deadlock. The bcast wouldn't necessarily deadlock because, for example, a valid implementation of a bcast would be an asynchronous send to all processes. I mean, it would probably deadlock, but you know, collectors must be called by all processes in the communicator. That's a classic error. I think computing everything everywhere is best. I prefer to use all reduce in preference to reduce, because if you call reduce, the value might only be known on the master, on the controller, but that's not obvious from your code. Because if we think of the pi example, where at the end of the pi example, only the controlling process 0, knew the value of pi, because we did the reduction by everyone sending to rank 0. But the variable pi was defined on every process. It just didn't. It was wrong on all the processes. So if you call reduce, it can be confusing because you have variables defined which don't have sensible values. So actually, calling all reduce tends to make things simpler. There shouldn't be any serious performance implications. So in general, I would recommend. Are you still hearing me? I had a slight audio issue there. Can someone confirm you can still hear me? Okay. So can you see the screen now? I think my network had a problem. Can people see the screen? It's back. Yeah, okay. I had a small network issue there. So in general, if you know, for example, if you use reduce, you have to remember that the value only makes sense on the root process. And in 3 years, you come back and look at the code and you say, oh, there's a value of pi there. That must be pi. Well, it might not. It's confusing. So I think it's okay. Error checking. So before, when we had all reduce, and if was this going to fail at some point? No, because everybody called all reduce. It just happened they called it, the even processes called it from one line, the odd processes called it from another line, but it worked because everybody called it all reduce. So that wasn't going to fail. If you'd have if rank is greater than 1, call all reduce, yeah, fine. And Dylan's asking, it's not defined whether this will deadlock. This will probably deadlock. Okay. It might not, because you could imagine a valid implementation of bcast would be an asynchronous send of X to every process. And so the root sends off all the data, and then, but it's unlikely. It will probably deadlock. It might not. It's possible it will give you the wrong answer. It's most likely. It's not defined in MPI. It's most likely to deadlock. But it's possible it won't. Does that make sense? But it's incorrect anyway. This is not correct. Okay, so I've checked for valid results. MPI reduced the partial sum 1 MPI float. If sum is less than 0, this isn't going to work because the sum is only defined on rank 0. So basically, this is incorrect. Okay, so if you're ever going to do error checking, you need to do global reduction. So what some people do then is they put a broadcast in there. Well, this code is correct, but you should never do that. Never use reduce plus broadcast, use all reduce. So what some people do is they do this. They write this code. But yes, if it was if rank equals 0, call all reduce, it will always end at a deadlock, yeah. But if you don't call a collective on every process, it will probably deadlock. It's not guaranteed to deadlock, but something like all reduce, where all processes have to actively take part, yes, it's guaranteed to deadlock. Yeah, does that make sense? Yeah. What some people do is they write this code. So, Jovi's asking this earlier question. Yeah. Is what the case? So I slightly lost the thread. So the code I give with the odd even was guaranteed to work because all processes were calling MPI all reduce. The fact they're calling it from different lines. The fact they're calling it from different calls is irrelevant. The MPI library cannot know. The MPI library doesn't know where you're calling it from. So whether you're calling from the same line of code or different lines of code is, the MPI library cannot make any difference because the library doesn't know. The library doesn't know where you're calling the code from. Normally you call, yes, they count as a single one. Yeah. Yeah. All you care is, are all processes calling all reduce? Yes, if they are, that's fine. The fact they're doing it from different lines is not significant. As I said, the MPI library actually cannot know what line you're calling it from. There's no way it can know. When I call a library call, the library call can't say what line was I called from. You don't know. Oh, okay. So some people write this, they do a reduce, and then they say, oh, I want to check the value, and then they realize this is wrong because the value is only known on rank 0, and then they put in a broadcast. Don't do that. Just use all. Okay. So I mean, I think if you use all reduce, it's going to be more clearer to write. Yeah. Send lots of small messages. This is I've seen people do this. For j equals not j less than j double plus MPI send x not j 1 MPI int. This is very inefficient. Okay. You should send a single message of size n. Okay. That's what you should do. Don't do that. Do that. Okay. But then the problem is you have what's happening with this. What would you do if this was a loop over I? This is a loop over I. I can't do n integers because the loop over I is not contiguous in memory. So if I wanted to do a loop over I here, how could I send a single message? I can't do a single MPI send, but I can do it as a single message if I'm clever. A vector, exactly. That's exactly why vectors were defined. Use a derived type, e.g. a vector for the equivalent loop over I. So you would do one myMPI vector, where hopefully this is defined correctly. But you should never do this, and you should never have loops over lots of small messages. It will kill your program. And that's why vectors and derived data types are useful. Of course, you could do a copy in, copy out, but it's not so elegant. Program specific, but some people, when they do the first simulation with the first solution to their Pi example, do stuff like this. Okay. There's two things which are wrong about this code. First of all, it only runs on 4 processes because you've hard-coded the upper limits. But secondly, you're replicating this code. Computer's supposed to make our life easy, and you're not supposed to replicate code all the time. So you should never write code which only runs on 4 processes. You may have other restrictions. It may need to be an even number or a power of 2. That's fine, but you should never write. Now, that doesn't mean that the number of processes can't be a compile time constant. It may not seem very elegant, but I mean, ideally, you write a program which runs at runtime, can run on any number of processes. The problem is, in real programs, different number of processes means different array sizes. By definition, if you do domain decomposition, as the process count gets bigger, the local array sizes get smaller. And sometimes it's much easier just to have P a compile time constant, so the array sizes are defined at compile time. I mean, it's up to you. It may not seem elegant, but it can make coding much easier, especially in C. So you should put the definition in the include file, and you should check at runtimes that size equals P. Okay. So that's not particularly elegant. It means you need to recompile your program every time you change the number of processes. But you'll see my simple solutions to the case study have that constraint just to make them really simple, right? But it's up to you. The most elegant code would run from the same executable on any number of processes. But having P a compile time constant isn't a disaster as long as you check at runtime. You say, hey, I've been compiled for 5 processes and I'm running on 7. You'll need to recompile me. That's fine. But you should never write code like this. Incorrect use of non-blocking. So I'm going to distribute this array to all these processes. So this would be fine if I use send and receive, but I'm using isend and iReceive. Why is this code wrong? Okay. It's wrong for two reasons, actually. Now start computation which uses X. There's no weight, okay? So what's the problem there? Exactly, Matthew, there's no weight. So what's the issue there? That's exactly correct. Yes, so exactly. You're going on to do the computation when you don't know if the data has been received, okay? So that's fine. So, but there's another, if we put a weight in here, there's another problem here. Every send does have a receive, yeah, because if rank equals 0, I'm doing else, everyone else is doing a receive. So I think every send has a receive. Have I written the code wrong? If you see, rank 0 is doing sending from I equals 1 to size -1, and all of the other guys are here doing a receive. So I think the send does have a receive. But there's a problem here with my even if I put weight in, what's the isend doing? I'm using isend and iReceive just as there's no reason here. I'm just using it as an example. So you're absolutely right, Jovi. You shouldn't be using. I actually come back to that. People but you shouldn't here. But I'm overwriting exactly. I'm overwriting the request. I have multiple non-blocking sends outstanding. I need an array of requests. I don't need an array of requests on the receiver because they only have. But on the sender, I need an array of requests. And this is a classic mistake. Yeah. It's like it's like you have to have an array of requests here, okay? So we need multiple requests on rank 0, and they must be weighted on at some level. But why use non-blocking here at all, okay? Exactly as Jovi said. People overuse them. Only use them if it's performance critical. Keep it simple. Use blocking routines when you can, when you're developing the code. The people overuse non-blocking all the time. Avoid this complication unless this is performance critical, or deadlock prone, but this isn't deadlock prone. We have a separate sender and receiver, so okay. Debugging, parallel debugging can be hard. Well, debugging is hard, parallel debugging can be very hard. The biggest mistake people make is they assume it's a parallel bug. So they run their program on 500 processes to get the wrong answer. They spend ages trying to debug the code. Actually, it might just be a plain old bug. They might just made a mistake in your code. So whenever you get a bug, don't try and debug your program on 500 processes. Run the serial code first. Run the parallel code with p equals 1. Then on a small number of processes. In most bugs, 95% of bugs will show up on 2 or 4 processes. Okay. It's very difficult to disentangle output. So being able to write to a separate log file can be useful. You want to turn this on, but having different log files for rank 0, 1, and 2 can be useful. Parallel debuggers exist. Linear it's now actually ARM DDT is more common, but it's a commercial product. And debuggers are powerful tools, but they're also very complicated and they're not magic. So your major defense against bugs is to write good code in the first place and have a good debugging strategy with test cases. Debuggers can be useful, but they're very complicated to use, especially in parallel. So you should print variables to the screen, okay? But people seem to write programs deliberately to make them impossible to do. This is my favorite. Someone says my program doesn't work. They type this, okay? No output. So you say, how far did it get through? I don't know. Did it read the input files? I don't know. Did it run for a minute or an hour, a second? I don't know. Of course, you might say, isn't it obvious it ran for a second or an hour? No. In a batch job, this is all the output you get. There's this style of programming which I simply do not understand, where people write silent programs. They never use printf. Impossible to debug a code, right? You have to write output to the screen to allow you to debug. So why don't people, I don't understand this, but it seems to be a programming style which is prevalent these days. You should write stuff to the screen, okay? So, it should say something like program running on 6 processes, right? We know it started. Whenever you read input file, maybe when you print data, you should print on what rank it is on. Otherwise, you don't. And then print out, if you have iterative loops, print out progress, but occasionally, every 100 iterations, Then just, this is the kind of output a parallel program should create. So that if it crashes, okay, then, then it's obvious. It might run for 500 iterations and stop. You might, well, why might that be? Well, in the batch system, you might have only requested an hour and it ran out of time, but at least you know it ran. If you don't print output to the screen, you have a program that's impossible to debug. So the other thing then people do is they write output to the screen and they write this and you get this, 135.6. Because the program has written this. They've written rank JX or in Fortran. You need to annotate your prints, You should have, rank 0x equals 5. Don't just write raw numbers. They're meaningless, okay? You should print out, So people write raw numbers. It takes an extra 5 seconds to annotate the right statement with what they are. And that will give you, you might remember when you put this print in what they mean, but in a month's time, you'll forget what this means. You want 135.6, don't know what that means. If you know that rank, but if you know that this is the right, so really, I know people say you can't debug with printf. That's a lie. You can debug. Other people's codes are different. If someone gives you a 50,000 line code that they have written and they ask you to debug it, you really have to start using debuggers and things. But to write, especially during development, printf is your friend. Print useful debugging message to the screen, which allows you to check your code is working. Common mistake, this is what people do. There was a bug. Okay, my code doesn't work. So I put a print statement in and now it works. Okay, I don't know why. Or I was compiling my code using the Intel compiler and it wasn't working. I started to use the GNU compiler, it was all okay. Okay, now, but I don't know why. All is okay. No, it isn't. There's a bug. You must find it, otherwise it'll come back to bite you hard. Okay. Don't just work. Bugs are bugs. Don't just say. I hate it when people say, "Oh, my compiler, my program only runs under GCC." Why? You've probably got a bug. Okay. Don't tell me what compiler. If you've got a proper, my code only runs under OpenMPI. No, you have a buggy code. So as soon as you find a bug, don't just circumvent it by changing the compiler or changing the optimization level, or putting a print statement in. You have to. And debug is an experimental science. Start with the serial code, then if you have a lot of good test cases, you will find bugs when you introduce them, and you can fix them. If you only test your code every 6 months, then you'll never find a bug. But saying changing compiler, changing MPI library fixes my code is not a valid statement. Your program probably has a bug, and you should try and find it. I mean, is my code working is a subtle question. We saw that a parallel program is very unlikely to produce bit identical results to your serial program. Now, the image processing example I gave you does give bit identical results. That's such a trivial algorithm. In general, a parallel program will not produce the same answer as a serial program. So our parallel pi code does not produce the same answer as the serial code, because the serial code adds the numbers up from 1 to n, the parallel code adds the 1 to n over 2, n over 2 plus 1 to n, and adds them together again. However, we're using floating point numbers. None of these answers are correct. They're all wrong to some level. They're only accurate. So we need to have some definition of acceptable, and that is difficult. Okay, so it is difficult, but however, so the output of your program is unlikely to be identical with any number of processes. However, if you run the same code twice on the same number of processes, you have to get the same result. Otherwise, that program is impossible to debug. Now, it's possible to write codes where if you run the same executable on the same number of processes, you don't get the same result. We saw in the Pi example, if we did a receive with MPI any source, we ran the same executable on the same number of processes, and we got different answers. Do not write programs like that. They are impossible to debug, because you have no, even for a fixed number of processes, you don't have you don't have a definition of what is correct. So it is difficult, but you know, a well-written MPI code should give the same answer every time you run it on the same number of processes. And to debug on different number of processes, you need to have some tolerance as to how variable should your result be. But if you have any numerical code, you change anything, okay, you're going to get a different answer. Yeah. So I mean, you know, you do the square root of x over 2, or you know, square root of, I mean, if you know, the square root of x over 2 is not equal to okay, the square root of x is not equal to the square root of x over 4. It is mathematically. Oh no, I've got the wrong way. Idiot. Root of x. Sorry, you know that. Sorry, what I meant to say was the square root of x over 4 is not equal to half the square root of x on a computer. Yeah? It is in maths. So, you know, if you want to take the square root of x over 4, if you take y equals square root of x over 4, y equals square root of x, they're different numbers. Yeah, they're different. So there's never a definition of the exact answer in numerical computing, but you need to have some idea of tolerance. But it is very difficult to debug in parallel. But you need to have lots of test cases which you test regularly. Optimization, you know, just like bugs which make your code incorrect, you should test regularly. You should, as you develop your code, you should keep running on your code on a number of input data sets with a range of MPI process numbers. And then if you put in some code which causes poor performance, then you will find out straight away. If scaling is poor, find out what the parallel routines are the bottlenecks. And again, there are profiles. I haven't covered them here, but there are tools which will tell you how much time your code spent in each MPI routine, standard profilers. Maybe the performance is poor, you need to work on the serial code. But the important point is, don't develop a parallel program for 6 months and then test its performance. You need to test its performance incrementally as you go along. So, are there any? I'm now going to talk about issues to do with arrays, and there's separate issues to do with Fortran and C. But does anyone have any questions about those slides? And I'll do the final few. So, MPI derived types enable strided data to be sent or received with no explicit copy and copy out. But a Fortran program would say, why not just use Fortran array syntax? Okay. Why not just do a Fortran program would just say, why don't I just do MPI send x of okay. Why don't I just, if I want to send every second element in the J dimension, I can just do MPI send x 1 to n to 2, because arrays are first-class objects in Fortran. Well, there are some subtleties for non-blocking operations. So I would actually recommend that is actually perfectly valid. What I've written there, MPI send x 1 to n, 2 is valid. But there are subtleties with non-blocking operations. So okay, fair enough. So what's wrong with this code? Allocate a buffer, call MPI send, and deallocate it. Or malloc, same in C, malloc, MPI send. No wait. So what's the there's no wait, but what would go wrong? You're absolutely right. There's no wait, but what would go wrong here? What could go wrong at runtime? Yes, because yes. So the MPI routine could decide, I'm not sending this now. I'll wait a bit. In 5 minutes' time, it decides to send the routine. You've deallocated it. So clearly that's wrong. However, so non-blocking send may still be ongoing at deallocation. Code could crash or give unpredictable behavior. Only safe to deallocate the memory after the matching wait. So you get identical issues in C using malloc and free. However, unfortunately, in Fortran, this arises in a more subtle way. So if I have this, okay, that looks fine. But what the compiler is probably doing is it's probably what the compiler does. So the MPI routine requires a contiguous block of memory. Right? So what the compiler will do is it will allocate a temporary buffer to copy in and copy out. So in general, array syntax is implemented through copy in, copy out. Now that is perfectly acceptable for a blocking routine, because by the time this is over, everything's fine. But so if this was MPI send, this is absolutely fine. But the problem is it's not. And so this code can give unpredictable behavior at runtime. So because Fortran array syntax is implemented potentially with copy in, copy out, because this is a non-contiguous dimension, it has to do a copy. So what are the solutions? It's only an issue for non-blocking operations. If you're using blocking operations, it's absolutely fine to use array syntax. Okay. So my advice is avoid array syntax even for contiguous sections such as columns. This statement here, the Fortran compiler will probably recognize this as a contiguous subsection and not do a copy in, copy out, but it might. So you probably want to use the old-fashioned syntax thing. But for non-contiguous rows, just use derived types. So array syntax is dangerous with non-blocking operations. So you know, I would recommend avoiding array syntax in non-blocking operations. So for contiguous sections, just pass in C speak, just pass the pointer, old-fashioned way. And for non-contiguous row things, you use a vector, and that's safe, as long as you don't deallocate the vector, of course. So, are there any issues? For C Fortran programmers, are there any questions there? The equivalent of C is the 2D arrays. So we've seen this diagram before. If we declare arrays as just int x44, in C we get this contiguous block of memory. So and the address C, the address of the array is the address of the first element. If we just do int x44, we're fine. The problem is a lot of people do this. Okay, they want to do dynamic memory allocation. So they say, well, we'll have float double star x is float double star malloc 4 times the size of float star, and then we loop over this and we do this. So the problem, so how many people do that kind of stuff? Well, it's perfectly legitimate. I used to do it. How many people have seen code like this for dynamic arrays in C? Yeah, okay. There's 2 problems here. First of all, the data is non-contiguous in memory. You've malloc these, you might call them rows, independently. So X is a pointer which points to an array of pointers which points to these rows. So we cannot now, I cannot send this entire array. If I wanted to send this entire array, I'd like to do MPI send X16, but I can't do that. Secondly, I can't use vectors, because vectors rely on this element being 4 from this. Yes, so I'm going to come back to that. So that is exactly the solution, Matthew. That's exactly the solution. But typically what people do is they do this. So data is non-contiguous. And the other point is, if you do an MPI send on X, if I do an MPI receive on X, I scrub over my pointers. So the trick is to do exactly like what Matthew said. We allocate a single block and we fudge up the pointers to point to the correct place. So you'll see in the solutions for the case study, I have an example called dynamic, where I've done dynamic array allocation, and I have a routine called aralloc, which is nice. So there's this routine called aralloc, which does exactly what Matthew suggests. You do a single alloc and set up double pointers. The nice thing about aralloc is it actually does one malloc, which includes all the pointers. So the other problem about this type of array allocation is to deallocate this. You have to deallocate it from the bottom up. You have to deallocate these pointers and then deallocate that one. But with aralloc, just a hacky piece of code I have, you can free it because it's a single malloc. So all it does is it does what Matthew suggests. It sets X to point. X points to these arrays, and it does all to these. This is a single block here, and you set up these things. The data is now contiguous, so that's fine. You can now use vectors or send or receive the entire array. But the important point is X is not equal to X00. You have to pass the address of X000 to to MPI routines, not X. If I do an MPI receive on X, it will start receiving and scrub over all these pointers and all hell breaks. I have to do an MPI receive on the address of X00 there. What do you mean it requires you to know the dimensions in advance? No, this is a runtime routine. So this could be M and N. So this is a runtime routine. It doesn't require you to know dimensions in advance. So the aralloc routine works for any number of dimensions. It says, give me an array of floats of 2 dimensions where the dimensions are 4 by 4. So I don't quite understand your comment, Jovi. This routine works for any number of dimensions where the dimensions can be any value. So you don't need to know. Well, yeah, but this could be M and N, where M and N are created at runtime. And I've just used this as an example, but in reality, you would use, this would be some runtime value. I've just put a 4 in here, but it doesn't have to be 4. It could be a variable. Does that? Well, you need to know that to allocate an array, you need to know its dimensions. Well, no, to allocate an array, you need to know its dimensions. Otherwise, you can't allocate it. So I don't understand your point. If I need an array of a certain size, I need to know all its dimensions. Otherwise, I can't allocate it in any sense. Well, I could, but it doesn't help me to delay the allocation. Why does it help me to delay the allocation till I know the other ones? It doesn't help me. I mean, you want to allocate an array, you need to know, if I want to allocate all the memory associated with an array, yeah, but it doesn't help. I mean, the fact you allocate the first dimension first and the second dimension doesn't help me. It's useless, really. I mean, in scientific and technical programs, you read an input file and you say, I need a complex array of 3 dimensions of size 53 by 95 by 82, and then you can allocate it. So yes, that's the way. So multidimensional arrays are a nightmare in C. C++ may solve it. I don't know. I'm not clear. Templating things. Are there proper multidimensional arrays in C++ that come off the heap, not the stack? Any C++ programmers want to correct me. Everyone seems to do their arrays in a different way, which is one of the problems with C and C++. Yes, but I'm sure it would be worse than C++. Yeah. So Fortran, no issues at all. Allocate is a feature of the language. So, but if ever anyone gives me a C or C++ program to debug, the first question you ask is, how are they allocating their multidimensional arrays? But you have to understand that before you can understand anything. But if you want to do equivalent of malloc for multidimensional arrays and use them elegantly with MPI, actually aralloc is a really good routine. So I've given you that code. But the other thing is X is not the same as the address of X00. So you need to get familiar with doing this. So the conclusions are run on a variety of machines, keep it simple, maintain a 0 version, don't see more bugs or parallel bugs, and find a debug you like. As I do say, good luck to you. But does anyone have any questions about that? Because that's really the last lecture. It's now going to be a practical session, and in the afternoon, people will be around to answer questions if you want. But that's really the end of the formal lectures. Does anyone have any questions? I probably won't be around this afternoon. I'll try and be around, but it might be a bit difficult. Actually, I think I probably will be around this afternoon. I think my diary has changed. That was my initial concern. I will be around this afternoon. Yes, I will be around. Other people will, but I will try and be around this afternoon. Yes, the videos will appear on the course page. They're just being processed just now, so they will appear. I hope I'm recording this lecture. Oh. Yes, I am. So the videos will appear on the Archer 2 course page. Yes, that's correct. So in terms of I just wanted to if you I found a website which can do this conversion. I need to fix this for good, but unfortunately I've run into problems with my, let's give me a second. Let's share. So the problem is that I use these PGM images. So you can see that URL there, image convert. I'll put that in there. So what we can do is if I run the, I just need to go to, if I, yeah. So okay. So the point is that my programs work with PGM images. Okay. So and the problem is that on Archer 2, PGM images are a very, very old format, and modern viewers might not. You can try, yeah, but modern viewers might not display them. Okay. So to view them, so my programs, the case study program reads and writes PGM images, which are nice old-fashioned text files. Unfortunately, many modern viewers won't view them, so you need to convert them to a PNG, and that I found this website which does that. So I can basically so if I go to, yeah, so if you haven't, when you produce a PGM file from the, I'll show you what happens here. Okay, I'll go through this in some. So I need to find the. Okay, that's view. So there are two issues here. Okay, so I'll show you the issues. So I'm looking for the source. Okay, so what I've done is I've downloaded. I'll now share the right window. It's very flaky today. I've downloaded the serial solutions. I'm just using the C1, same for Fortran. Okay, so this is the serial solutions for the case study. So it reads in something called edge 2x128.pgm, and it implements the algorithm which I've gotten. So this is available for you. This does this image reconstruction. Okay. And writes it out, but it writes out this PGM file, and I give you a file copy. So let's compile this. Make. Okay, so the make file is set up for, unfortunately, set up for Intel. Let's use GCC, and I run it, and it produces an output image 192x128.pgm. What I can do is I can drag that into this website. Now, you may not be able to view that. You may or you may not. But I can drag that into this website. I'm sorry, okay, there we are. If I drag this file, which you can't see, of course, into the website. It's really not happy today. And to convert, you'll see that that's the output. It's a picture of the Loch Ness monster. That is what the output should look like. Now, unfortunately, you cannot look at the input files directly. It's a technical reason, which I'll show you. This exercise is maybe needs to be simplified, but I'll show you what the issue is. The issue is, yeah, it's actually not Nessie. It's actually there's supposed to be another monster called Morag in a nearby loch called Loch Morar. But yes, it's the equivalent of Nessie. If you look at the output image here, which I wrote, okay, it's just the pixel values. It's saying this is a 192 by 128 image, max value is 255, and these are the values. That's why I like PGM files. They're nice and simple. The problem is that the input image, the edge image, has negative values in it. Okay. The reason is, remember, the edge is the second derivative of the image, but that can be positive or negative, so I need to retain that information. And some image viewers don't care, and some care, and this one worries. But what we can do is that we can just run for 0 iterations, because my output routine fixes that. So if I set max iter here to be 0, make. So if I run for 0 iterations, I can view the input. Apologies for this; it's a slight technicality. Doesn't seem to. Oh, I know why. I need to run for 1 iteration. Sorry. 1 iteration. Sorry. Yeah. So if I now view this, so unfortunately you need to run. So with the normal image viewer which I had available, none of these problems arose. But unfortunately, with the recent move to Archer 2, which has been rebuilt recently, the image viewer on Archer 2 doesn't do what I need. So I apologize for that. But you can see the output image there, and if I now show you what the input was, it looked like that. So that was actually, so you can see it looks like the edges, basically. That looks like you maybe could have guessed what the image is, but the output comes up as a. So I will send some instructions. I'll try and simplify this. I'm trying to install the correct viewing program in Archer 2, but hitting a few issues. But at the moment, you can view the output images as PGMs either via this website, or a lot of image programs will view them, and we've seen here that the Mac sees them, which is nice. How does the Mac view the input, the edge file? So the edge file has negative values in it, which is something which some of the image viewers don't like. I need to retain them because I need to differentiate between positive and negative edges. But someone said that Eric said that the preview So you see, yeah, okay. So different PGM is a very woolly format, and different viewers. Some just take the absolute values, some complain. So if you're on a Mac, you're fine. I will try and fix it for other people by getting things working on Archer 2. But if not, there is that. At least for the output images, you should be able to. And what I'll do now, actually, let's just. If I've also given you. I've also given you the code, the parallel code to look at. Which I've just downloaded. So MPPK solutions. If I go to see, oh, I didn't unpack them. /C MPI, for example. You'll see that I've hard-coded the number of processes in here, but the code basically runs, it does scatter, this just implements the algorithm. What I wanted to do here was to comment. Now, I've done the communications here with MPI send receive, but I would recommend that you did it with non-blocking send and receive. But if I comment that, remember my original suggestion for the parallelization was to do everything but the communication. Let's comment out the communication. The make file is wrong again. This is all on my laptop, so MPI run -n 4./image MPI. It runs, and now let's see what that looks like. So if I basically convert that again, let's do it. So this is what you'll get if you follow the instructions on the sheet. This will be your intermediate answer. Let's drag and drop it. You'll see that we get exactly what. Oh, that was the wrong. That was the wrong file. Sorry. We get exactly what someone predicted. That if I do this partial solution, you can see here, and that's why I like. Can you see that? Okay. Yeah, that's why I like image processing examples, because you can debug your parallel program visually. I got the halo swaps wrong here. In fact, of course, I didn't do them at all. But if you can see here, you can see these vertical lines, and you can see immediately that the image was split up into 4, as I've drawn it here, vertical slices. But because we didn't do the halo swapping, we got the wrong answer. Yeah, and that's quite a nice sort of visual debugging tool, and that's why I quite like these using images, because it does allow you, modulo the difficulty of viewing them, I can look at it and say, look, your halo swaps are wrong. You can see immediately because there's this big line here. So I hope that was interesting. So I've gone on slightly longer than I expected, but if you're following the timetable between now and lunch, which is at 1 o'clock, people can work on the case study. You can look at the sheet or work on other exercises if you want. And in the afternoon from 2 till 3:30, there'll be people around to answer any individual questions you have. You will get emails asking you to fill in the feedback form, which will be a praise feedback form, because this is a praise course. I'll be really appreciate it if you did that in, if you filled that in, because obviously I'm always interested in feedback on the MPI course, but we've run this in a number of different formats, and this format is this slightly blocked up lecture practical with a few days in between, and I'd be interested in your comments on how that went. We're still playing around with what different formats for this course, but I hope you found that enjoyable. I will try and be around this. There will be people around this afternoon to answer your questions. I will try and be around. I think Queven is definitely going to be around till 1 o'clock. Is that okay for you just now, Queven? I have to dash off. Are you're free until 1, aren't you? Excellent. So Queven will be around till 1 to answer your questions. And hopefully, if I get this image stuff sorted out, I will circulate something. At the moment, we'll just have to live with it and cope with the fact we can't view the input files because some of them, the negative values, and you have to use this image convert if your machine doesn't support viewing. I will try and get this installed in Archer too. Apologies for not noticing that till too late.